So this one's going to be a little bit about science and magnets, basically. Obviously, everyone's played around with magnets at some point, hopefully. If you didn't, you had a deprived childhood, because, oh my God, they puzzled me so much, and they still do. But anyway, there's a channel called The Good Vibrations on YouTube. You can look it up. On it, he shows lots of examples of how magnets induce some kind of or whether they induce or that is what magnetism is. But there's like a kind of vortical field, let's call it a field for want of a better word, but there's a vortical field around these magnets, and he demonstrates it in numerous different ways using very simple experiments that anyone can do at home if they've got a little bit of electrical knowledge. I don't have any of my electrical stuff around, so I can't reproduce his experiments for you, but you just need to go on his channel. There's loads of them. It really, there's one of them, for example, to show that there is a kind of vortical phenomena around the magnets. He has a magnet with the north pole facing the camera, another one with the south pole facing the camera, electrical wire loosely held in front of these two magnets. He puts it on a current, and the wire that's opposite the one pole goes up, and the wire that's near to the other pole goes down, due to the fact that you've got on one magnet you've got a spin going that way, on another magnet you've got the spin going that way, and obviously because they're going two different directions, one forces the wire up and the other one forces the wire down. It's a very simple experiment. So yeah, that's introducing the idea of vortices to you and their relationship to magnets. Now, I'll do one actually with some little magnets on at some point. I haven't got any here, but I'll get hold of some. But there's another thing you can do, a little simple experiment you can do, in a bath or a bowl of water or something. You can get a plate or anything flat and just move it gently through the water. And you've probably noticed in swimming pools and things like this, or when you've rowed a boat, you get these little vortices that form at the periphery of the flat object as you move it through the water. And they go down into the water. They're like little vortices. They get narrower as they go down, and they go in opposite directions. So one goes clockwise and one goes anti-clockwise. Is that what I'm doing there? Yeah, they're going different ways, aren't they? So yeah, what's that got to do with magnets? Well, if you think about these two vortices, one going clockwise, one going anti-clockwise, and you think of the north and the south of a magnet as being two different spin directions, one going clockwise, one going anti-clockwise, then you have what in effect is what you're looking at in the water. If you imagine the magnet poking up, you've got one pole that's going one way, one pole going the other in the water. Now the thing is with these vortices, and you can show it with putting a little bit of dye in to the centre of one of the vortices, they're connected under the water in a half of a circle. So you've got a anti-clockwise vortex going one way, you've got a clockwise vortex going the other, and they somehow meet in the middle. So you're probably thinking, so what Well, the thing is, if you just have, you've got to cope with the idea of chirality here. Chirality is the fact that you can have a rotating, so this is like a spring shape. If I turn that spring looking at you, as you're looking at it, that's going in a clockwise direction, like the leading edge of it is going clockwise, isn't it? Now if I keep turning that the same way, I'm not changing the direction of the way I'm turning this. Now the leading edge is going in an anti-clockwise. It's sort of dragging behind. It's going that way. So you'd think that these two vortices, one going clockwise, one going anti-clockwise, is a straightforward kind of a single thing, turning in a single direction, and with kind of, bent around like in a little loop like that, and one is going one way, one's going the other. Now that might seem to make sense, but if you think about this shape here, bend it back into shape, into a little spring. If you're familiar with an Archimedes screw, right? So this is going, again, let's do it. That's going clockwise. It's got a bit bent now. That's going clockwise, right? So that little bit there is kind of like burrowing into the water, if you like. So it wants to pull in, screw into the water like that, like a screw. It wants to screw in. So in an Archimedes, what should we call it? Spiral? I forget what they're called now. Archimedes screw. This end is like in the water, and it's going that way around, and it's drawing the water up through the centre, and it's expelling it out that end. So if it was just a straightforward case of a single thing going in like that and up like that in the water, then you wouldn't have two dimples, would you? You'd have a dimple one side and a bulge the other. So it can't be as simple as what you might at first imagine. So here I have prepared one. So here you've got two vortices going in opposite directions, as you can see. Right. Now then, if we want them both to be sucking down, which is what is happening, then this one would kind of need to go kind of that way, so you're kind of hypnotized into it, and that one does the other. So they've both basically got to go in opposite directions in order to suck the water in. And as soon as you start thinking about like that, these are going like that, and then you start turning them in opposing directions, you realise that in the middle, this central bit is going to just lock. Like there's a familiar to some people, maybe not to others, there's a thing called a turnbuckle. So it's got a left-handed thread on one end and a right-handed thread on the other, and a hook on the end of each. And there's a thing in the middle, like a thing like that with two threaded bits in it, one left, one right. And so as you turn the central bit, it winds both of these screws into the centre. Now, when both these screws hit the middle, then they lock. Right? It's not like they could ever continue through and out the other side, because one's left hand, one's right hand. Similarly with this. So if you imagine these are going around under the water and meeting somewhere in the middle, they're going to lock up in the middle somehow. So you've got two opposing vortices, and there's what is this? What's going on in the middle of these two vortices? When they meet, somehow they're one thing, but when they meet, there's a kind of a null point. Is the only way you can think of it logically. You know, what if I was to join these two together into a continuum, you would end up, as they kind of wind into the middle like that, they'd end up having to do like a little loop up in order to keep their shape. So these two bits here would have to sort of join by going, I don't know if I can even do that. Sort of up like that in a little, I'll try to get it clearer. So they'd do sort of like that in the middle. And they'd be joined by a little kind of loop that went over from one to the other like that. It's the only way you can think of what's going on. There's logic just drives you towards the idea that there's this sort of weird reversal thing that goes on in the middle. So if you look at magnets, going back to magnets now, you've got these two vortical spins, one going right hand thread, the other one left hand thread, and they are going to have a kind of a null point in the middle, which is what you find in a magnet. So in the centre of a magnet between the two poles, there's a sort of non-magnetic bit, which is where this kind of null point is in these two vortices. Now the weird thing about magnets is that you can they're a kind of inherently fractal object, and without getting into all the, you know, how people sort of think of them as working, atoms with spins and all that kind of stuff, just looking at them as an object in our normal world, you know, if you break a magnet, so you've got a whole magnet, and you can kind of, you might think of the North Pole and the South Pole as being the two halves of the magnet. But if you break a magnet in half into two pieces, you don't get two half magnets, you get two whole magnets. And it doesn't matter how many times you subdivide that magnet, you've always got whole magnets as part of the breaking down process. You never end up with one pole over here and one pole over there. You know, they're essentially, they turn into two magnets. So that's enough, I think, for now, but just a little bit to ponder on the nature of magnets and their divisibility and how they might represent something that, although it appears to have parts, is actually a single entity, and how it just gives rise to other fractal versions of itself. There are some, if you check out the channel, there are some little videos of the things in the water, the little dimple things. They're called half-ring solitons, and there's some videos of me making some. And what you see is that they, as well as the little dimples, you get like it looks like a jellyfish shape. So you get this sort of leading to spirals going forwards, and you can't get a leading edge that's sort of like a curve that sort of like goes in advance of these two little swirling vortices, and then through the centre you get this sort of trailing sort of shape like that comes out with like tendrils, like a jellyfish. This looks like a jellyfish. Yeah, so there's some videos of that, and a half ring soliton is essentially one half of what you can do if you're a smoker and you're good at blowing smoke rings. You can puff out these little vortices that are actually stable vortices, and they're in a loop, and they sort of go forwards like in this sort of unfold. And there's some really good YouTube videos of people doing these smoke vortices, and they shine through them with lasers, so it's like it's sort of almost like a kind of a X-ray of the inside of this vortex, and you see this same jellyfish shape. It's like it is, the two things are completely related. But yeah, anyway, we'll get into the even more strange things about magnets when I find the ones that I add. But anyway, that's a little venture off into some little science that you can do at your own leisure in your own bathroom, and put some dye in and see that these things are actually linked, and then think through how how you have a clockwise vortex, an anti-clockwise vortex, and what on earth is going on where they meet in the middle. It's like it'll blow your mind. I'll tell you, it blew mine. I mean, just look at me. So yeah, it's a little thing you could do with the kids as well. You know, they like it if you got kids. You know, they love that sort of thing. Anyway, there you go.